Okay, we can start. Good afternoon, everyone. Thanks a lot for joining us for our PowerWeb Lunch Lecture series. I'm Francesco Lombardi. I have the pleasure to host and moderate this lecture series. Before jumping into today's topic, as usual, for those of you who might be joining for the first time, let me spend just a second on introducing PowerWeb, which is the organization that promotes this lecture. So PowerWeb is a place at UDelft where we do what we cannot do in individual faculties. We join forces between electrical engineers, mechanical engineers, people from technology policy and management, industrial design, and so on and so forth, to achieve the goal of supporting the design of intelligent, integrated, and inclusive energy systems, which go beyond what individual disciplines can do. Now, when it comes to intelligent, integrated, and inclusive energy systems, intelligence is nowadays at the forefront because we have so many developments in artificial intelligence and quantum technologies that could make our systems as flexible and versatile as needed to achieve the energy transition. Today, we're going to dive deeper into this topic with a global leading expert in this field, which is our distinguished guest, Professor Kumar Venayagamoorthy, who holds professorship positions in various institutions, among which Duke, Clemson Universities, and a few others. And he is as well a distinguished member of the IEEE organization, where he chairs committees on power system controls, among others. So without further ado, I'm going to give the floor to our very welcome speaker. Please, Professor, educate us and entertain us with your lecture. And if you have questions, we will have a Q&A session at the end. Thanks a lot.
Thank you, Francisco. Good afternoon to all of you. I hope the microphone is working here. Yeah, I think so. Yeah, hopefully. So it's a pleasure to be here this afternoon to give a talk at TU Delft. I've been here for some time collaborating with the Center for Systems and Control with Professor Bart. So we have a NSF, US NSF National Science Foundation, European ERC project collaboration. So that's how I'm here. So this is my second visit, and so glad that I can give another talk. This afternoon, I'll be talking about some of the research that we have been doing in my lab, the Real-Time Power and Intelligence Systems Lab, first formed at Missouri University of Science and Technology, where I was there from 2000 to 2011. Then moved to Clemson University from 2012 to current. Yeah. So this lab was formed, Real-Time Power and Intelligence Systems Lab, RTPIS lab for short, was formed in 2004, based on my vision at that time that the power systems will need AI. And I've been working in AI for the last 31 years, applied to power systems, right from my graduate studies back in South Africa, where I got my PhD at the University of Natal. And my master's thesis and my PhD thesis was in developing neural networks in hardware to control electrical machines, precisely turbo generators. So, so I presented a lot of papers and a lot of talk in the 90s when AI in power systems were thought of as a fictional study. But I'm glad that today a lot of people are using AI. So my presentation is outlined as follows. I'll briefly introduce the topic for this afternoon, and then I'll get into adaptive critic designs, and then cellular computational networks, and then briefly in the time permitting, quantum computing for power systems. How many of you are familiar with adaptive critic designs? Yeah. How about cellular computational networks? Yeah. And quantum computing, I'm sure quite a few. Yeah, okay. So I think it'll be interesting. So I'll start with the introduction, and I'm sure many of you work in complex systems. And complex systems basically can be the brain, for example. Here we have a biological neural network, basically a picture of the brain taken under a high-resolution microscope. The cortex of a rat brain. You can see how the neurons are connecting based on some stimulus. And then the other picture, yeah, Yeah. So what you see here is the burst in the brain due to learning and how the neurons are connecting. It's a highly nonlinear system, spontaneous behavior. And of course, we have other examples of complex systems, transportation network, air traffic, and then, of course, the transmission system of the US North American power system. As you can see here, it's highly complex. And of course, today, I think the internet connections have overtaken the North American power system because it used to be known as the single largest machine ever built by man until the internet has overtaken it. So dealing with complex systems, networks, modeling them, optimizing them, controlling them is always a challenge. And this is back 2003 in the US. The blackout that we had, that was a massive one, 60 gigawatts of load loss, more than 50 million people affected, and basically comes down to lack of situational awareness in control centers. At that time, SCADA was being utilized in the monitoring of the power network, and SCADA basically streams data around 2 seconds to 6 seconds. Today, we have phasor measurement units. And phasor measurement units, synchrophases, basically stream data at about 30 hertz to 60 hertz, depending on what frequency. So a lot of data today. The North American power grid has more than 5,000 PMUs and 30 hertz, 30 samples per second. That's lots of data coming per second from all the PMUs. So back then, it was a lack of situational awareness because we did not enough data to comprehend what was going on in the control centers. And today, it is a lot of data, and how do we make sense of the data, right? So it's not much of a difference. Before we didn't have data, and we were looking for data. Now we have a lot of data. How do we process and make sense of the data faster than real time? So it's not about having a lot of data. It is all about how we turn data into information, information into knowledge, and how we get understanding from the knowledge. And some of this can come from shared view, collective, collaborative analytics, and so forth. Yeah, and to connect the right dots is what matters in a time-critical way. So models are very important in any complex system, especially the power system, because the dynamics are always changing, right? It's a highly dynamic, complex system. So developing a model is key. And the kind of model that we want is also one that is accurate all the time, and one that also has a multi-timescale resolution. Richness, right? You can get right down to milliseconds, to seconds, to minutes, to hours, and so forth. So when you think about such a model, then basically we call this a real-time wealth of knowledge, because wealth means richness. Real-time means up-to-date, accurate to the point of time that you are controlling. And then you basically, once you have such a model, then you need 3 strands of thinking, and one of them is sense making. So that is important to make sense of the data, to have that understanding. And then, of course, you want to make decisions. That is the second strand of thinking. And then eventually, whatever decisions you come up with, you want to implement it on your physical power network or physical system. And then you have some adaptation, and that means not everything in the set can be implemented. So you have some physical constraints that you have to adjust them. So you go through this cycle of sense making, decision making, adaptation, having the model as the center of all of this. And we call this the computational systems thinking machine, CSTM. So, since my talk is on AI mostly, I'm going to go back to computational intelligence. The IEEE has Computational Intelligence Society. We don't have an AI society. And the Computational Intelligence Society emerged from the Neural Network Council, which became a Neural Network Society and then eventually name changed to be CI. Okay, so computational intelligence basically can be, computational models and tools of intelligence that can take this large raw numerical data from the synchrophases, from IoTs, and be able to process them in a very fast way, whether it's in a parallel or distributed way, to generate reliable just-in-time responses that are highly fault tolerant. And some of the CI paradigms can be artificial immune systems, evolutionary computing, fuzzy systems, neural nets, swarm intelligence, and then, of course, none of this by themselves are superior to on every single problem. So basically combining them, forming hybrid systems eventually will be more powerful. So you can have, for example, neuro-fuzzy systems, neural networks with fuzzy membership that can have more flexibility. So CI basically is what you're going to see in most of my work this afternoon in my presentation. So I'll go to adaptive critic designs. Adaptive critic designs basically mimic brain-like intelligence, the ability for such tools of intelligence to cope with large number of variables in parallel, in real time, in a noisy, nonlinear, non-stationary environment, which is what the power system is. And the origins of ACD, adaptive critic designs, they are basically synthesized from ADP, approximate dynamic programming, reinforcement learning, and then, of course, using neural networks to get real-time derivatives. That way, you can basically have an actor-critic system, and your neural networks can provide real-time derivatives to learn the policy. And, in optimal control, we basically solve for the Hamiltonian Jacobian-Bellman equation, and adaptive critic design is a way of doing this iteratively. So whether you're doing control, whether you're doing optimization or scheduling, if it's a dynamic problem, that is your actor. It can be a scheduler, controller, optimizer. And the critic basically is the network that approximates the Bellman's equation of dynamic programming, the cost to go function, J. And then, of course, if it's a complex system and it's a dynamic system, then you want to have that real-time model that I talked about, mimicking that. And then you can use that to get your derivatives and update your controller to learn that policy. So the critic can be of two types. One can be just a scalar critic, where the cost to go function is J. And in this case, the beauty of the adaptive critics is that it's self-learning, right? So you can basically put two critics in two time steps, and it can learn over time, given a utility or a reward function. So it's a self-driving learning system, okay? So it's forward learning and not backward learning. So that's why we use J. J here is an approximate of this equation. The other one you can have is the more powerful one. It is not the scalar J, but it is the vector J. And in this case, you are basically learning the derivatives of the cost to go function with respect to the states, which is lambda. And the derivatives critic, known here as the DHP, dual heuristic programming, is much more powerful than the HDP, which is the scalar J. So there are so many different versions of this, and you can have a combination of both, where you have the scalar and the vector, which is much more powerful than any of the two, but much more complex to develop as well. So I'm going to show you a few quick applications of this adaptive critics in power systems. And here is a New York, New England benchmark, IEEE benchmark power system, New York power system, and New England power system. So a total of 16 generators, 68 buses, 5-area system, and the rest 3 areas here are the New Jersey, Maryland, and Pennsylvania PJM system. Yeah. So one of the problems we have in this system is we have some oscillations, inter-area oscillations, especially on this when something's change on this major transmission corridors. between New England and New York. Basically, you have some inter-area low-frequency electromechanical oscillations. And we want to design a damping controller, K. And of course, we have a thyristor control series capacitor here. And we want to use that to basically minimize the oscillations in some of these lines, 51, 54, 18, 16, and 13, 17 shown here. So how do we design that K controller? And basically, we chose the adaptive critics approach. This is also known as a wide area controller, WAC. And there's a cost function. We use the scalar critic here. And basically, I'm not going to get into the design details of this, but it is all reported in this paper. This was a study done with Imperial College, the control group there in the electrical department. And they took an approach to design an H-infinity controller and also a state feedback controller. And we took the adaptive critics, the HDP. And some time responses shown here, settling times, overshoot. And here is some frequency response. And you can see that the HDP controller, which is the black line here, seems to basically outperform both H-infinity and as well as the state feedback. So that shows the adaptive critics is a data-driven approach, learning-based approach, and we can basically design a good controller. And this is a three-phase to ground fault, a typical fault. Another application that I like to share with you with adaptive critics is the optimal power flow. And many of you might be familiar with optimal power flow, but here we are talking about AC power flow, dynamic stochastic OPF, and doing this every second to 2 seconds. So normally you would have your OPF done and set points dispatched maybe every 5 minutes. And what we're doing here is to basically use a wide area monitoring system. Now that we have phasor measurement units, we can get samples every 30 hertz, 33 milliseconds. So 1 to 2 seconds is feasible to every 3 samples. And then we can design one of these DHP or HDP controllers, and then basically come out with delta signals to the set points every 1 to 2 seconds. And that way we can control the power system more closely, more better. You can see here for a disturbance, this was basically a trip. This is for a 12-bus benchmark system that we're looking at here. For a trip of one of the loads, the frequency goes up, and that basically causes some line flows to change. And as a result, you can see that with the conventional black line here, conventional control, you are exceeding the 1 per unit limit. And whereas with the DS-OPF, which basically is replacing the AGC and a secondary voltage controller. And here you can see with the traditional approach, the active and reactive power controls are decoupled the moment you get into the secondary control. And in the primary control, they're further decoupled. Whereas DS-OPF couples both active and reactive power. And as a result, you can see the improvements in the frequency, the red line, the tie line flow, maintaining the line flow limits. And this is also another example of a different case study where we have renewable energy variation. And you can see with the DS-OPF, the frequency is almost 60 hertz, whereas with the AGC and the secondary voltage controller, the frequency dips are higher. There's a lot more details in this paper, and this has been scaled up to larger power systems in a follow-up paper. Okay, so this is the follow-up paper where we scaled it up to the 68-bus system, where we show that such DS-OPF controllers can be done in a hierarchical way, hierarchical distributed way. So every area can have a DS-OPF controller, and then we can have a global DS-OPF controller to coordinate the area controller. So basically, you can scale this up. And here we show for wind fluctuation, how the area and the global controllers can keep the line flows within the limits, the red line, and also you can see how the frequency control can be done better with the area controllers and area and global controller compared to the traditional approach. So, and this is because it's a data-driven approach. We are monitoring the system with PMUs, we're getting those samples, and this is a learning-based controller. So it is much more affluent on the dynamics of the system. Moving on to another example of using adaptive critics to a microgrid. Here we have a microgrid, just a small case study with some wind turbine, with some photovoltaics, some energy storage, some backup generators in case of everything fails, and then grid connected and can be grid islanded. The loads are classified into ones that you cannot curtail and ones that you can curtail that can go through demand response. And furthermore, if you want to expand on your energy storage, you can bring in electric vehicles, and we call this smart park. Smart park is a parking lot where you can perform two kinds of transactions, grid to vehicle, which is the normal charging, and then of course V2G, which is the discharging. Yeah, so you can expand the capability of the microgrid if you have a parking lot called smart park, for example. So we want to design a dynamic energy management system, and basically you want to try to have some set of objectives, and the DEMS basically has to do the dispatch such that whatever objectives you set in can be met, and then you have a way to measure whether those objectives are met. So some of these objectives could be as follows. You want power to the critical load at all times, right? 100% reliability to the loads like hospitals and so communication towers and so forth. At the same time, you want to maintain the battery's SOC at an optimal level for the sake of having 100% reliability to the critical loads on days when you have a lot of cloudy days and a lot of rain, and then it becomes cloudy, then you depend on your battery for supporting the critical load. And at the same time, you want to maximize the utilization of renewable energy resources, wind and solar, and limit on the using carbon-based resources. You also want to maybe limit on importing from the grid because the microgrid wants to be more self-sustainable, and maybe even export back to the grid if you have extra, clean energy. You also want to make sure that the controllable load that you're controlling here, you don't want, a controllable load could be a power to a movie theater, a cinema. And of course, we all understand that cinema and balance of life is very important, right? So if you cut the power to the cinema all the time, social life is cut out and the customers will be unhappy. So you want to put that into the objective function and maximize controllable load, more customer satisfaction. And yeah, so, and of course, batteries are expensive, and therefore you also want to be aware of the fact that batteries have finite life cycles. And if you charge and discharge so frequently, if you do bang control on the battery, then you kill the battery and then expensive. So you want to put all of this into a mathematical equation. And basically you're saying that you want to design a DEMS where the microgrid will be self-sustainable, it will be reliable, it will be environmentally friendly, and it will be technology ready for smart grid functionality. By that, I mean you can also extend a microgrid to a network of microgrids. If you set up microgrid clusters, then they can handshake, it becomes a network, they can connect, and then they can transact. Then you get into transactive energy. So here we design again using adaptive critic designs. And adaptive critic designs, basically, here is the ADHDP, where the scalar. And you can see all of those objectives that I talked about, it's been put into the utility function here. Critical load, non-critical load, the battery life, the use of the unclean energy diesel generator, grid connection, the cycles on the battery. This is the battery discharge. Right? This is the non-critical load. So all of those could be put in and weighted depending on. So the microgrid operator can change this utility function depending on what is needed for that day or for that week, right? And this learning-based controller can tune, yeah? A lot more details in this paper. So here I'll show you, here's some solar wind profile for 2 days. And here you can see the performance of the DEMS, 2 types of DEMS. One is the decision tree DEMS. A decision tree is just based on an expert saying how you're going to control this, and you fix rules. It's very static, whereas the adaptive critics approach is the IDEMS, intelligent DEMS, and you can see the performance, the red bars versus the blue. And you can see on the second day how the DEMS is actually doing good, outperforming the decision tree-based DEMS. So the one way to measure how good these controllers are is to come up with a performance measure. And what we are looking at here is how much of renewable energy was utilized to meet the load demand. So if we have a certain load demand and you use renewable energy to meet that load demand, you can't ask for more, right? Perfect, right? And the second one is an indication of how much of controllable load was met. So controllable load, if you remember, is your cinema, right? And if there was no curtailment to the cinema and you're able to watch your movies, then that is even like heaven, right? So that is the best you can ask for, right? So here I have a normalized PI, performance index, which is basically this divided by that. And you can see it's greater than 1, which means that always the intelligent DEMS outperforms the traditional priority controller. And here is the initial battery SOC percentage. Yeah? And here is the battery size. And the battery size can be flexible because you can bring in smart park on top of your fixed battery storage. But if you find the sweet spot, okay, and the sweet spot is somewhere here, you can get 25% to 30% more performance for the same hardware capital investment. Software, brain-like intelligence, can all of a sudden pop up with that, finding the sweet spot. Okay? So that's one way to look at it. For the same capital investment, using brain-like intelligence, you get 25 to 30% more performance because you are using brain-like DEMS. Or you can say that if you want the same performance, you can downsize the microgrid sizing. Okay, so it depends which way you want to go. All right, so that's the beauty of this ACD. All right, so I'll move on to CCN, cellular computational networks. So I talked about the CSTM. I'm sure you still remember the computational systems thinking machine, right? I talked about the model and the 3 strands of thinking. So when you think about the North American power grid or any complex system, it's humongous, it's big. So how can we take AI to basically a large system, a large complex system? It's going to be difficult, right? Just to say everything is going to be driven by AI. How do we do that, right? So that takes us to distributed CSTMs, where you can have several of CSTMs coexist in harmony, coordinated, and they're communicating. So basically, you can build CSTMs for a microgrid, for different microgrids, each with its own CSTM. For the distribution center, the system, distribution systems can have their own CSTMs, then eventually different regions or areas of transmission, and then power plants, right? So you can imagine the entire power grid or power system with a population of CSTMs. And that is basically how AI can actually manage the entire grid. You cannot design one AI system for the entire grid. It has to be, distributed AI. Okay, so eventually for each of the CSTM, digital twins will become important, right? At different levels, right? At the component level, at the subsystem level, and then eventually at the system level. The abstractions will be different. So digital twins will be key to successful operations and management of complex systems. So if you take the power system with all the different nodes and cells, had the distribution, and then several of this eventually make up the substations down to the distribution, then transmission. With a lot of IoTs now, you can get data, right? So developing real-time models, the kind of models that I talked about, real-time wealth of knowledge, or those kind of models can be developed with AI tools, and basically you can have digital twins at different levels that basically form a hierarchical. This digital twin of the whole power system will be a number of them at different levels, different granularity, and then they will basically allow us to implement distributed intelligence. Also, digital twins have to be up to date, right? The digital twins are basically mirror of the component or the subsystem. That means as the component ages, the digital twin has to capture the aging as well. The performance degradation, for example, in a battery has to be captured, so you cannot command the same kind of current that you want from a battery when it is in its first year compared to its fifth year, because it won't respond. Okay, so everybody is using AI, right? In one way or the other. And when you talk about today's AI, it is basically neural networks. What sits in AI, in the AI engine, is neural networks. Yeah, and maybe some fuzzy representations, and maybe we evolved the neural networks, or some kind of evolutionary approaches are there, and maybe we make the neural networks more robust. Maybe there's kind of immune system inside the neural networks, right? We put some safeguard rails to protect the data in and out, so that attacks won't happen. So all those you can do, bells and whistles, but the core engine is neural networks. Yeah? So what is a neural network for those that may not be familiar? We have a multi-layer perceptron here, very simple feed-forward neural net, inputs, hidden layer, and an output. Inputs go through maybe a linear transformation, then in the hidden layer they go through a nonlinear transformation, and then they get summed up and you get an output. And then basically you get input-output data, and you basically learn parameters between this input layer, hidden layer, and output layer, which are known as the synaptic weights. Like for example, here we have a 2-input neural network, 1 output, 1 hidden layer, 2 weights here in the input layer, 2 weights in the output layer. So when you have the y and x data, you learn these 4 parameters. They're known as weights. Once you have learned them and the training is finished, you have an equation for y as a function of x, which now involves the neural network weights that you have learned. So after training, a neural network is no longer a black box. It's a white box after training. Before training, it's a black box. Okay, so there's always in the community thought that, oh, neural networks are black box before training. After training, it's white box. Unless the data changes, then you keep tuning. Yeah. Okay. So today, a lot of neural network work is on deep learning and deep neural networks. Correct? Sure, some of you are using deep neural nets. And what's the difference between this and this? Only difference is that we have several hidden layers, right? Several hidden layers with millions of neurons. It leads to a lot of parameters. Yeah, a lot of parameters means that a lot of data to train, and a lot of data to train means a lot of training time, and a lot of training time means a lot of energy to train. That means if you're going to use a deep neural network that takes several weeks to train on large data to develop something as complex as maybe ChatGPT, this becomes an energy-hungry beast, right? So those of us working in energy, trying to make energy systems efficient, should think twice before we use deep neural networks. Are we going to consume a lot of energy? Because we are trying to save energy, efficiency, trying to use renewable energy, right? Trying to mitigate climate effects, right? So why would you want to burn more energy to save little energy. It's like taking one step to use AI to improve energy efficiency and taking two steps backwards to burn more energy. Right? Think about it. So my suggestion is think about it very carefully before you use deep neural networks that consume a lot of energy and a lot of data. So what can we do that's different than that? Can we come up with shallow neural networks that use less energy, more sustainable AI? Right, that takes us to CCNs. Okay, CCNs are cellular computational networks that use computational units connected to each other in an ordered distributed manner. And basically, they're cells, and the cells can be used, the CCN as a network can be used to model complex systems with temporal and spatial dynamics. Basically, a generic cell consists of three units: a computational unit, a learning unit, and a communication unit. A computational unit can be a neural network, can be just an algebraic equation, can be a differential equation. And the learning unit is if it's a neural network, is just finding those coefficients of the neural net. And the communication unit is to basically handshake between the cells to connect them. Yeah. And you can take a complex system and you can break it down into subsystems, and subsystems can be modeled by cells, or you can even break the subsystems into components, and components can be modeled by cells. So you can build your digital twin from the cell, bottom-up approach. And basically this minimizes the size of the neural networks that goes into the computational unit. Your computational algorithm becomes more efficient when you break down and you put it together. So for example, if you have a network of 4 inputs and 4 outputs and 4 nodes as connected as shown here, we can use 4 MLPs to model that. In this case, after modeling, the MLP is decoupled. Each of them is decoupled. So if anything changes in this system, this cannot capture. To solve that problem, we can use a recurrent neural network with 4 inputs and 4 outputs. And yes, this models that. But if this becomes 1 million inputs and 1 million outputs, then this becomes a deep neural network, and that's not what we want. But with the CCN, we just model the input and the output, and then only the connectivity. And it is basically a sparse recurrent neural network with a lot of sparse weight metrics and less data. So that's one of the ways in which we can benefit instead of using a deep neural net. And the other thing is that with the CCNs, if you're using a CCN to model a complex system, let's say you have a CCN with 4 nodes, and this is the topology of the connection. If a disturbance occurs at cell 1, that disturbance based on the topology will only propagate in the next time step to cell 2, and then eventually from 2 back to 3 and 4. So the propagation of disturbance is based on how the propagation in the CCN is based on how actually it propagates in the physical system. And if the performance of a cell degrades, then you can basically use a tuning algorithm on the cell itself, and you can monitor each and every cell. Whichever cell falls below a certain performance threshold, that cell parameters will be updated and not the whole network, like in the case of a deep neural net. So you have sparse learning, and that saves a lot of time. Not only fewer sparse weight metrics, but also sparse learning. Yeah. So these are the nice things about the CCN. It's cellular, modular. The training, computing can be done synchronous or asynchronous, very efficient, easy learning. You can implement this in a distributed and a parallel way. It's scalable. You can add cells and delete cells. The performance, if a cell falls below a certain threshold, the performance degradation is graceful. It is resilient if it has been attacked. If a cell has been attacked or a section of the power grid has been attacked, the entire CCN doesn't fall apart. Last but least, the most important, it is a sustainable AI approach. So I'll show you quickly in the interest of time, maybe like 5 minutes, yeah. A couple of case studies. So one of them is the distributed Voltva control. Maybe some of you might be familiar with. Here's a distribution system. We have modeled that using a CCN. And based on this, this is the IEEE 34 bus distribution network. We have brought in some 3-phase and single-phase solar PV. And what in this problem we are trying to do is distributed Voltva. So we are basically using this reactive power the curve here, reactive power with voltage, this is normally fixed in an inverter, and we are trying to tune that when a number of inverters, IBRs, are in a distribution system so that they can be in more symbiotic. So basically, we do an optimization and find the different voltage points, and as an ecosystem. That is the problem here. How can we all have them work together to do this volt-watt control? Different solar profiles changing, different load profiles. So first of all, you can do for each of these volt-watt curves, you can provide the parameters from the optimization. And basically, then you have the cell CCN representation where you can do the optimization. So each cell, a number of nodes that is trying to minimize that voltage deviation, then as a whole distribution system, collectively a number of cells. And this is the cost function we are trying to minimize. And of course, you can see without the CCN approach, and then with the CCN approach, we have two types of optimization. One is looking at which cell, which IBR has more higher sensitivity, more response, and the other cases where we're just going through from it, since most of the distribution system will be radial, we're going from basically the ones that have from the first to the last. So the two approaches, a graph optimized approach and an impact, and you can see the impact, the ones that have higher response capability are doing well. And you can see optimized voltages compared to unoptimized voltages. So that's an application of handling a lot of complexity in a distributed way using the CCN approach. The other case study I want to share with you is the cyber attack, denial of service attack. So this is going to the transmission to area formation with PMUs and of course AGC, automatic generation control, on both the two area system, each one having its own AGC. And basically PMU7 provides the frequency feedback to AGC1, PMU9 provides the frequency feedback to AGC2. AGC1 is also doing tie-line bias control because besides maintaining the area 1 frequency, it's also controlling the power that has been sent from area 1 to area 2. So if there was a fault on bus 8, this is the time when an attacker would disguise and attack PMU7, right? That way you don't know whether it was the fault that is causing the disturbance or whether it is the attack. So, and if you just had the fault, it will be the blue line. The fault plus the PMU7 being attacked, denial of service attack for 100 packets, you can basically destabilize the system. And the frequency, basically feedback is lost, and that's why this is AGC1 cannot control. But now we use the CCN to do a virtual synchrophasor network. For every PMU, we develop a virtual PMU. So these are the cells. And now cell 7, which is the virtual PMU of PMU7, kicks in to provide the frequency during the fault. And this is utilized by the AGC. And you can see that without the attack is the blue line, and with the attack and the CCN approach is the red line. So you don't see the difference. Behind the curtains, the CCN has taken care of it, and the frequency has been, feedback has been provided. This is 300 packets blocked by the attacker. We studied this from several packets more. Amount of tie-line power that is lost is almost zero with the CCN, whereas with the conventional approaches, basically lose the system. Okay, so last part, very quick, quantum computing for power systems. So my group has been working on quantum computing. Our first paper was on 2004, in applying quantum computing to power systems. We basically started with quantum-inspired AI or quantum-inspired, some of the AI, computational intelligence. So some of the work that we have done is taken, for example, particle swarm optimization and brought the concept of quantum computing, basically the uncertainty principle. If you know particle swarm optimization, you basically have particles that have velocity, that are moving, and basically positions. But we now switch to the quantum uncertainty principle and basically say that the PSOQI differs from the standard, in fact, that the exact values cannot be determined, and we use the basically map it into a search space, and then when we want to measure the velocity or when we want to determine the value of the velocity or the position, we basically go through the collapsing. And we brought in this concept of the delta potential well-based probability density function to accelerate basically the search in PSO and basically help the convergence. So we basically changed how we compute the position of the particle, bringing in this concept of the attractor point, using the current search, and then using quantum principles basically to enhance, or to say have a mutation, further exploration and exploitation. And then we basically compute, particle swarm optimization is a population-based technique. So we use the mean best, and then we get this attractor point, and then we are able to find better positions for the particle, which leads to better near optimal, so-called optimal solutions. So with this kind of algorithm, PSO-QI, we are able to basically go back to the power system, some of the things that I've shown you for wide area monitoring, where we have a different kind of neural network here. I don't know if you're familiar with SRNs. They're basically simultaneous recurrent neural network. The difference between simultaneous recurrent neural networks and recurrent neural networks is that in the recurrent neural networks, we have a unit time delay. In the simultaneous recurrent neural network, there's no delay in the feedback. So we take here is a hidden layer feedback. It's taken into the context layer without a delay. So some of you might be wondering, how is that possible? But our vision system works that way. The only way you can see me standing is because you have a simultaneous recurrent neural network in the vision system, visual cortex, right? What happens is that the frequency of the feedback is much faster, several orders faster than the frequency at which the input is changing or the input output is calculated. So this kind of has to stabilize before an output is calculated. So this type of simultaneous recurrent neural network is very powerful for learning complex dynamics. So, and again, it's very difficult to get an SRN trained. And here with the PSO-QI, we are able to apply that for a wide area monitoring system, SRN based. And we show the difference when we use just a standard PSO and a PSO-QI in the convergence, and some of the accuracies are better. So that's one of our early works using PSO-QI. And now we are basically, we have an ongoing project we just started with one of my collaborators at Penn State. So now we are taking, now that quantum computing has become alive, a lot more we can do. We are basically going into looking at all kinds of different power system problems, electric power transmission network modeling using PMU data. So that means we don't even have to know the topology of the power system, and we are able to use the PMU data to infer the topology. So this has multiple applications. We can basically use data to know what is in the field and how what should be in the control center. Then we are also looking at contingency analysis. We are also looking at OPF with lots of IBRs in the system. And then, of course, most of this are basically, this is a quantum neural network because we have a lot of the quantum algorithm, QAOA, basically has trainable or tunable parameters, which is like a neural network. And we can basically learn those using, this is a variational approach with classical and quantum. And we can basically try to find the best circuit to speed our results. So we are in the process of doing a number of things. In the interest of time, I will just stop here and say that hopefully I've shared with you that distributed intelligence it has come across, and CCNs, and then emerging computing technologies. Last but not least, I'm also the editor for IEEE Press on Energy and Power and Energy Systems. These are some of the books that we have published in the last 3 years in the series. So if you have an interest in publishing a book, please email me. Maybe you're finishing a dissertation or you're finishing a project and you want to share that results with the community. The IEEE Press is one way to do that. Last but not least, I'm the Vice President for International Neural Network Society. If you're passionate about AI and you really want to know how to develop brain-like AI, which is more efficient than the AI we have, I invite you to join INNS. And I will be the International Joint Conference on Neural Network 2027 General Chair, which will be in Cape Town, South Africa, a beautiful place, June 14th to 18th. So if you like to go to Cape Town, South Africa, you have a good AI paper that you want to work on. You have about a year plus to start working on it, and hope to see you there. Thank you.
Thanks a lot for the presentation with so many cutting-edge methods and application. Let's open the floor to the questions. Yes, I'll walk to you with a microphone so that.
Thanks a lot for the lecture. I'm a very small, I would say I'm a novice at computational intelligence. I just had a very simple question on what is the difference between CCN and computational neural networks? Sorry, cellulose computation networks and cellular neural networks.
Yeah. Okay, so cellular computational networks, thanks for the question. So our earlier papers were CNNs, cellular neural networks. Then we make it more universal, generalized, CCNs. Because if you still remember the slide that I showed with the generic cell has 3 units, the computational unit, the learning unit, and communication unit. So the computational unit doesn't have to be a neural network in all the cells. So if it is a neural network, you can call it cellular neural networks. And if it is some other algorithms, it's cellular whatever. So the algorithm can be anything. So after a lot of work, we said this CCN can have heterogeneous algorithms. You don't have to throw in a neural network when it's not called for. Neural networks are good for nonlinearity approximations and learning. But if the problem is linear, just put a linear algorithm in the CCN. So you can mix and match. So then that's how we changed the name to CCNs.
Okay. Yeah, because I think we are trying to record the lecture, which that's why it's helpful to have this.
Yeah.
Yeah, very general philosophical question almost. Although, yeah, neural networks are very powerful to do a lot of different things, but they're very difficult to explain in terms of what they're doing, why they're doing something. When you have very deep networks or very complex networks like the ones that you're showing, you have even problems with getting trapped in local minima. There's a lot of problems there, and there's very powerful reason why they are not being used for anything safety critical. But you're actually proposing to use them for something quite safety critical, our whole power distribution network. So my question is, we have very recently a massive blackout in Spain. It took a month and a half to figure out exactly what happened. And even then, with classical control methods, classical systems, we don't totally 100% understand what happened. What are the consequences of moving to things like what you're proposing? I mean, aren't we then just trading a potential increase on performance for having very little resilience and even less possibilities to diagnose problems or to do forensics?
Yeah, very, very excellent question and very important question. Yeah, so of course, if somebody who is going to deploy AI in safe critical systems has to really understand the safe critical systems to begin with. Yeah, that's very important. If you don't have the domain knowledge, and I think you cannot just blindly apply AI. There are a lot of people who know AI but don't know the domain, so you cannot do that. So both two are important, understanding the dynamics, how the control works on the power system. As I said, if you're going to develop an AI for the power grid, you have to do it in a distributed way. And neural networks are safe. if we can put guardrails in the input and the output. So to do that, we need to understand the operating range, the safe regions, and you can tailor the design for power systems or any system. If you know the domain, you can do it, right? In my opinion, if AI systems were controlling the power grid, the blackout in Spain wouldn't have happened. Okay? We can agree or not agree, right? So because the AI systems would pick it up, will flag it, will mitigate it, will change their control set points, and take it care of, right? So it's very important for engineers, power system engineers, to understand AI, and AI scientists to understand power system dynamics. These two come together, you can design safe systems. I work in hardware. I control real machines with AI. I have a paper back in 2002 where I control micro machines that mimic the South African power systems with DHP learning controllers, 2 learning-based controllers controlling 2 power plants. So it takes one to, you have to understand both and to design it.
Okay, thanks a lot. Because we are a little bit over time, I would suggest that we close the official Q&A session here, but we can continue with the formal Q&A session. If you have more questions, perhaps Professor Venayagamoorthy can spend 5 more minutes here. But at least let's close the official session for those of you who might have other meetings. Thanks a lot again, Professor. Brilliant presentation. Thanks a lot.
Thank you.
And on the way out, you'll see a QR code to give us feedback and insights for future presentations. So please do that. We always welcome your input. Thanks a lot.